Greetings and salutations, magical chemists. Let's talk about the glories of gases. Before we dive into gases, we need to talk about the variables that we measure about gases. And the first one is pressure, represented with the letter P. This is just the force per unit area on a surface. More specifically, the pressure of a gas is the force that gas exerts on the walls of its container. An instrument known as a barometer is used to measure atmospheric pressure. So when you see terms like barometer or barometric, it basically applies to pressure. The thing about pressure is there's a lot of different units. Now, in pre-AP, we also talk about units of kilopascals, but those aren't actually really tested in AP, so I should not have left those on there. Whoops. But we are going to focus on atmospheres, millimeters of mercury, and torr. You may or may not remember that millimeters of mercury and torr are the same dang unit with just two names. Why? I don't know. And you do not have to memorize these conversions. They are given to you on your delightful formula chart. Another important variable for gases is temperature. Temperature, of course, the letter T, is a measure of the average kinetic energy of particles in a given sample. Now, you may recall that kinetic energy, abbreviated Ke, is the energy of motion. So the hotter something is, the faster its particles are moving. Kinetic energy is given by the equation 1/2 mv squared, which is given to you in your formula chart, where m is mass and v is velocity. It's extraordinarily important that you recognize one fundamental thing. Temperature is directly proportional to kinetic energy, which means if you have two samples that are at the same temperature, they have the same average kinetic energy. Notice how big and bold those words are? It's because this is really important and a very common question that is asked on the AP test. All right, you are probably excited to learn that we can also use particle diagrams with vectors to illustrate differing kinetic energies, and thus different temperatures. If you compare the difference between the low temperature vectors and the high temperature vectors, well, the longer the arrow basically represents a greater kinetic energy. It is moving faster. Now, there are multiple temperature scales that you need to be familiar with. Of course, Celsius, which is based upon the boiling point and freezing point of water. Water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius, which is why, it's a very useful scale to have because those are numerically easy to remember. But the problem is, if you're talking about temperature being the energy of motion, you need to have a 0 temperature be the temperature at which all motion stops. And unfortunately, that's not 0 degrees Celsius, right? Because you can get colder than 0 degrees Celsius. Not often in Texas, but it happens to us sometimes, as well we know. So the scientists use a temperature scale known as Kelvin. Now, Kelvin does not get a degree symbol, it's just K, because it's actually based on something real. It's not a kind of arbitrary unit like, water. No, the thing about Kelvin is it is basically Kelvin is 1 degree Celsius. They're the same amount of temperature, but we've shifted it. So 0 in Kelvin is what is called absolute 0, the lowest possible temperature there is. And that amount of shift required is exactly 273 degrees Celsius, or 273 Kelvin. So water freezes specifically at 273 Kelvin, and it boils at 373 Kelvin. And then, as I mentioned, absolute 0, that's the theoretical lowest temperature possible. And where all motion stops. Crazy. Now, it is very easy to convert between Celsius and Kelvin using this handy-dandy formula that is given to you on your formula chart. Basically, take the temperature in Celsius and add 273. And then one more thing about these variables of pressure and temperature. There is conditions that are known specifically as standard temperature and pressure, or STP. This is defined to be specifically 1.0 atm of pressure and 273.15 Kelvin. So if you remember this from pre-AP, be careful. We're getting a little more specific here. It's not just 273 Kelvin. It's 273.15 Kelvin. But worry not. This is, of course, given to you on your formula chart. Okay, there are two factors that affect the velocity of gas particles, and you have to know about both of them. The first one is the mass of the particle, And the second one is, well, it's temperature. Let's talk about temperature first, because, okay, so this graph, we're looking at the second graph, and we are assuming we are taking the same particle, sorry, I over-highlighted there, the same particle, and we're comparing it at different temperatures. This is a Maxwell-Boltzmann distribution curve, but remember, you're just looking for the average, because they're going to change, they're going to be variable, but we're looking about at the average. Well, at a lower temperature, 273 Kelvin, sounds warm, right? But it's not, that's 0 degrees Celsius. On average, the velocity of the particles is going to be going slower, but you heat it up, and of course they are moving faster. Temperature is a measure of the average kinetic energy. So the idea is you heat them up, you speed them up. Things are getting a little more interesting when you start looking at different particles at the same temperature. At the same temperature, they of course have the same kinetic energy, but remember that kinetic energy is equal to 1/2 mv squared. So if we're comparing particles of different mass, for instance, oxygen, conveniently located, so oxygen out of all these has a relatively high molar mass, notice at the same temperature, on average, it's moving more slowly than, say, something like hydrogen. Very, very light molar mass, so on average it is moving much more quickly. This is because at the same temperature, their kinetic energies are equal. But of course, their molar masses are very different. Hydrogen has a much lower molar mass than oxygen does. So for this equality to be true, that must mean that oxygen is going much more slowly and hydrogen much more quickly. So to summarize, if they're at the same temperature, heavier gas particles are moving more slowly or are slower than lighter particles. Although, of course, this is only true at the same temperature. And then, if we were considering the same gas particle like we did in the second graph, well, it's going to be going more slowly at low temperatures and faster at high temperatures. Okay, let's dive into kinetic molecular theory, otherwise known as KMT. Now, there are 5 specific postulates of kinetic molecular theory. Ideal gases are assumed to behave according to these postulates. Okay, well, the first one says that gas particles are really, really small, and the space between them is really, really large. This means, relative to the giant spaces between them, gas particles have a negligible volume, and we can basically ignore it in calculations. This also means gases are highly compressible. They have large spaces between them, so it's easy to squeeze them together. All right, second postulate. Gas particles bounce off walls and each other with no loss in energy. These are known as elastic collisions. And of course, it's the force of the particles hitting the wall and bouncing off that gives you gas pressure. For the third postulate, we know that gases are the highest energy state of matter. Because they have so much kinetic energy, the gases are in constant, rapid, random motion. Can't stop, won't stop. Okay. Also, gas particles do not attract or repel each other. This means you may be delighted to know that we are assuming that gas particles have insignificant or basically negligible intermolecular forces. So they can easily glide past each other. Basically, this is because they're moving so quickly, they're already past each other before they would have even noticed that they were attracted. All right, last one, and we've talked about this. The average kinetic energy of a gas is proportional to the velocity of its particles. This is that whole heat 'em up, speed 'em up, all over again. Okay, well, those are the 5 postulates of kinetic molecular theory, which is how we assume ideal gases behave. It might not surprise you to learn that ideal gases are imaginary, because no gas perfectly fits all of the postulates of kinetic molecular theory. A real gas, however, well, doesn't exactly match all of KMT, and it thus does not behave appropriately. In AP, you definitely need to know a little more about real gases than we did in pre-AP, but not that much more. So more specifically, let's look. Okay, so we know that things that are polar have stronger IMFs, and ideal gases aren't supposed to attract each other. So the more polar a gas molecule is, the more it will deviate from ideal behavior. And in fact, because the gas particles are actually attracted to each other, the pressure is going to be lower than predicted. At low temperatures, IMFs will also become problematic. Basically, they don't have enough kinetic energy to overcome those intermolecular attractions, so once again, pressure will be lower than predicted. Pesky IMFs. Something else you can do to make a gas behave less than ideally is apply high pressures. One of the postulates of KMT says that the volume of a gas is negligible, but if you squish them with a high enough pressure close enough together, then the distance between them is no longer negligible. So volume in this case is going to be higher than predicted because the gas particles are actually taking up notable amounts of space. So here's a graph of this. Notice the idea: at low temperatures, pressure is lower than predicted. So if you measure xenon, as opposed to this theoretical ideal gas, it's going to be just a little bit lower. But notice, it's not that far off. That's why, assuming and doing our calculations with ideal gases, it actually works pretty dang well. And then in the other case, now at high pressures, now the volume's going to be bigger than predicted. This time we're looking at argon, so if you squish it enough, now you have non-negligible volume. So let's talk about when gases behave most ideally. Well, they're going to behave most ideally at high temperature because the kinetic energy overcomes the IMFs. And they're also going to behave ideally at low pressures because the gas particles are relatively far apart. And of course, they'll behave ideally when they have relatively low IMFs because, they're not going to be attracted to each other. So that means you're looking for things that are small particles and they are non-polar. So you will be expected, if given data, and you're like, hey, here's this pressure, but it's supposed to be blank, to predict what could have gone wrong. So notice, if the issue is that your pressure is lower than predicted, there are actually two potential reasons. Either, basically, your temperature is too low, you don't have enough kinetic energy, or your IMFs are just really, really high. And this is, of course, because of those pesky attractive forces between particles. Of course, if your volume is too low, that actually could be caused by the same thing. It is basically too cold of a temperature, or those pesky IMFs are too strong. Notice, so things that could cause low pressure or low volume, basically IMFs. You love them. But last but not least, if your volume is higher than predicted, that actually could only be caused by one thing. Your pressure is too dang high. Well, you're squished into a tiny container, which of course means high pressure. And that's because you are going to have particles that are non-negligible in volume. Okay, last but not least, we need to talk about Graham's law, basically of diffusion and effusion. Although they sound very similar, actually they are very similar, but they do have different meanings. Diffusion is just the spontaneous mixture of gases, or mixing of gases. Effusion, however, is very specific. It's the passage of gas through a very tiny hole. This is like gas escaping through a tiny hole in a balloon. But they're both related to the same thing. They're related to the velocity of the gas particles. Now, because we know at the same temperature they will have the same kinetic energy, and kinetic energy is 1/2 mv squared, you can rearrange this and look at the rate of your gas movement, aka your velocity, and it's going to be proportional to 1 over the square root of the molar mass. You don't actually have to do the math for that. Luckily, all you need to know is that lighter gases, things with a lower molar mass, are going to both diffuse and effuse more rapidly than those that are bigger at the same temperature because they have a higher velocity. But be careful. Lighter doesn't necessarily mean smaller. Heavier doesn't necessarily mean bigger. So watch out for your language. You want to say lighter or heavier. You do not want to use the language of bigger or smaller because it's directly dependent on mass. So let's try a quick couple of practice problems, and then you'll be done with this video. Okay, so we're going to take two 1-liter balloons at standard temperature and pressure. So notice they are the same volume, same temperature, same pressure. One is filled with helium and the other with carbon dioxide. So there are 3 practice problems to try. I want you to go ahead and try them, and when you're ready to check your answers, unpause the video. Hopefully the first one was easy, because yes, of course they have the same average kinetic energy. They're at the same temperature. They're at standard temperature specifically. A little chilly, but note that we said average kinetic energy, because the absolute kinetic energy, it's going to vary from particle to particle. Okay, let's look at the next one. Well, in this case, hopefully you recognize that no, they do not have the same average velocity because helium atoms have a lower molar mass than carbon dioxide molecules. So, at the same temperature, helium atoms will have a greater average velocity than carbon dioxide, and it's because the kinetic energy is equal to 1/2 mv squared. And I do actually see AP answer keys like that. They're like literally because kinetic energy is 1/2 mv squared, and that's enough. You don't have to actually do the math. This means, of course, the helium balloon will deflate first because the lighter helium atoms are effusing more rapidly than the heavier CO2 molecules for the reasons we just talked about. Ta-da! And you are all done with the first video and ready to move onward and upward to the glories of gas laws. I'll see you there.